Hey everybody, how you guys doing? Happy Tuesday. Got a couple things on tap for today. Let's turn the volume down a little bit here. There we go. All right, so we're going to talk more about trees today and the third individual project, which I think will actually be our last individual project. I was hoping to get 4 in here, but that's okay. I think we'll do this last individual project and then we'll move on to the final project. So we've got all of April for that. Otherwise, I think we're just packing too much in. So, and that'll be okay. That'll be okay. So we'll talk about the lab first, and then dealing with trees here. The idea was we're going to try and take our tree and try and do that positional wrapper. And we want a way for someone to be able to navigate our tree. So I just asked for you to add a couple methods there for it, interacting with those. Oh, I forgot to close my door. Give me just a second. There we go. All right, so I'll spend a little bit of time on trees. Yeah, I got a little bit of yogurt for lunch here. Yep. It's been one of those days. But I do have my coffee, so that's good. My little guy is not feeling well, so it was a rough night. He was up till about 4:30 in the morning. So, but then he slept in a lot, so that was good. Okay, so we had our entry here, right? And this is just using a list and going through here, and we looked at depth, we looked at height, we looked at whether or not we're a leaf, because this makes our height be a little bit faster here, because we just need to check the height of our leaves here. What they do with the tree is we're a hierarchy. We usually draw them upside down, so we start at the top, and we draw all the children, and then the grandchildren and great-grandchildren, on and on and on, whatever that hierarchy looks like here. So this was a way to look at the tree, and then we were going to add a couple methods. Right? Let's pull up the lab here. And this was like right out of the textbook, kind of following along, but doing with an N tree. He didn't actually implement those with an N tree, so I thought that might be more interesting for us to try. Okay, so root, give the position of a root. So again, we need this position wrapper class. The idea is that we have another class for position here, and that we're actually going to interact with this one. So we have a class position, and then init takes a bunch of things. So we're actually going to go steal this wrapper, because I don't want to have to rewrite it all again here. But we did this for our linked list, right? The positional linked list, and we can use most of that same position idea here, right? Not all of it, but a lot of it here. So let's look at position. Okay. There we go. So we should just be able to paste that in. There we go. So there's a class for position. Right, when you create it, you give it the container. Now we don't actually need a node, right? We need to we have the tree itself, right? So maybe we'll call this a tree. Yeah, and it is its constructor. Tree, and what did tree have for its value, right? Tree.value. And other tree is tree. Okay. Yeah, just this idea that we can have a position, it belongs in a given container, right, which is it is a position in the parent tree, and then it has the tree data itself. Okay. What does it not like about this one? A number of lines or something? That's fine. Okay. Oh, so we had add child, we had that. So now we're going to add a couple of those methods. So we wanted to create a position from the root. Where is it? Here we go. Okay, so let's take a look at some of these here. Oh my goodness, that did not paste well at all. Why didn't that paste well? Nope, okay, it just doesn't want to paste. That's fine. That is okay. So we'll do them one at a time. So we'll define a root method. I know, right? Just does not want to do it. So it returns the root of the tree, or none if t is empty. And we have a isRoot method to figure out whether or not that position is the root here. We have a parent, so we can get the parent position. We have the number of children. We have an isLeaf, and we have an isEmpty. Yeah, empty's none. We have nothing. So here, let's work up from the bottom here. So define our isEmpty, and that is a tree. So T for tree here is empty, right? The P is position here. Position, 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 position. Right? So if our tree is empty, we don't have any positions. So if our value is none, right, we could say return value equals none. Okay, if our value is none, we're empty. We're an empty tree. We have no value or self.value. We must be an empty tree. We can check that, or maybe we have no children. I don't know. And self.children. What the length of self-children is 0. So we have no value and we have no children. That's a pretty empty tree there, right? Okay, is leaf for a given position. So again, we're going to need some of those helper methods, right? We're going to need a way to convert the position, right? Validate it, make sure it belongs to our container, right? And then get the tree out and get its children. We can do that. So let's define is leaf for a given position. Right, so we should have, if it belongs in me, we should have the same root. Right, well, okay, so we need to figure out how to get the root then. So how do we find the is root of a position and the root position? Sure. Okay, let's do root first. So define root. Okay. So remember, we can walk these links here. If we have a parent, we're not the root. If we don't have a parent, we're probably the root at this point. So we can say, you know, self dot. Actually, no, we are a tree, right? So if self parent is none, self dot parent is none, and we want to return it as a position, right? That's us. So we're going to return a position, and we need to give it the container and then the actual tree itself. So self and self, right? We're the main container. We're the head of it here. Self.position, and we're the current tree that we're looking at. Remember, like each tree, because it's recursively defined, the root here has a bunch of child trees. Each child tree has a bunch of child trees. Each child tree has a bunch of child trees, on and on and on, until they become leaf nodes. Right? You could look at each one and say, okay, it's the tree rooted here, but yes, it has parents. It has this whole collection all the way up there. So if you ask for the root position of a tree, great. Or none, I guess, if the tree is empty. So we can do that. So if, yeah, we'll say self.is empty, return none. Otherwise, we can return ourselves. So if we're empty, return none. Otherwise, return a position of our root. Right, that's us. Okay, so is leaf. So we need to validate this position, get the tree back out, and see if it has any children. Right, so we've got root, and then we had an is root as well. We wanted to find is root of a given position. Hey, Stray Robotics, thanks for coming on by. We're having some fun here looking at trees, an end tree currently with this crazy positional wrapper. It's a little bit messy, but that's okay. We'll appreciate the other trees we look at after we've done this one here. So if you give me a position, right, we want to see if it is the root or not. Right, and we can compare positions, right, to see if the trees match. So we can return position equals self-root. Right? If I go get the root and compare it to the position you gave me, I'll figure out whether or not I'm the root tree. Right? If our trees are the same, yeah, we're the same. Okay. We've got root. We have a parent of a position. Okay. So if we ask for a parent of a position, we'll come back to is leaf. So define parent of a position. Oh, again, that's right. We need the validate position, right? So we're going to make sure that we can validate position. given a position. And the same kind of idea here. We did a validate position over here. Where did we do that? Validate position. Here we go. So it checks a couple things here. There we go. So if it's not a position instance, raise a type error. If the container is not self, it's not valid, right? It doesn't belong to us here in our tree. If the node next is none, okay, we can skip that one. Okay, return the tree. And return its tree. So let's validate our position here. So we have the the current tree equals self.validate position. And then we can return, it might be none, right? Oh no, that should be fine. So then we can return the current tree parent, no, current tree dot parent. Because remember, tree has this parent value here, and it might be none, right? And we want to turn that into a position, right? So self.position. And so who's the container? Well, the container is our root, right? So we need self.root. And then the tree, then that we're wrapping around in this position, is the parent of our current tree. Okay, so isLeaf, again, we're just going to validate. So we have a current tree. Let's validate our position. Oops. And we return current tree.children. Length of current tree.children equals 0 if you have no children, right? You're a leaf. As we even use the isLeaf here, right? Why not? Return current tree.isLeaf. Right, because current tree is a tree, so it can tell us if it's a leaf or not. Might as well. We don't have to repeat that logic there. I should say is none. Okay. There, that made that one happy. Okay, what other ones are we missing here? Number of children for a given position. Okay, number of children for a position. Define number. What was that? Num children. I hate that. Number of children for a position. I like that better. So we need to validate it. Right? And then our current tree children. We want the length of that. Right? Does this make sense at all? What we're working through, kind of navigating this end tree idea. So all of our stuff works. We haven't done any of the other things yet here, but we should be able to get a position, right? Get its number of children. We should be able to ask for that, right? So let's ask for that tree's root. Let's see. So we want print root dot, and we want, oh, that's the root position. Okay, so let's do that. Let's do root position. Dot position. And let's print. Now we want root dot. Now some of these things need positions, right? So we want, say, like number of children given the root position. We should see how many children we have. Oh dear. Let's see. Oh no, it's dot root. That's right. So I called it root is our tree, and then the method is root. Okay, that's a little funny there. Let's try that. All right, so we have 3 children, right? Which I think makes sense because we've added 3. So we have our root. We added a child here. We added a child here. And we added a child here. Okay, so the ones I'd asked you to skip then, right? We weren't going to do any of the ones that iterate. Okay, we just wanted to add some of these. The ones that iterate are a little bit trickier. So you need to look at how we do some of these iterations here. So like t positions or iterator of t, or actually getting the children, T children from a given position is a little bit trickier. But we can do those. Okay. So if we wanted the children then of a given position, so define children of a position, where the idea here is we want to iterate over each one at a time here. And now we have some, remember we've looked at this yield keyword before, where it's going to give you something and then wait for you to ask for the next one in an iterator. I think this was a little while ago, but we had that. Right, so we'd say for child in self.children. Oh, I'm sorry, from a position. So you need to validate the position first. Validate the position, and then for child in current tree.children, want to yield, oh, sorry, I can spell yield right, child. And we want to turn that into a position. So self.position, and the container is self.root, and then the tree is the child. So you should ask for each child here in the position. So if I do that, then we could say for child in root dot children of the root position. Okay, the idea is everything we interact with comes through position here. When we interact with our tree, we should be interacting with the positions, which is just going to make life a lot easier for us. So we'll say for every child in the children of the root position here, let's just print the child, see what we get. Right, and they should toString with their value here, so we should get a couple values out. See what we get. Uh-oh. List is not callable. Root children. Oh, we messed this up. Child. Oh, that's okay. In children. Oh, what did I break it? I broke it. Oh boy. Let's see. Sorry, I'm trying to find my child here. That should work. Why is it? What am I doing wrong here? That's okay. That list object is not callable. Dot children. Let me try debugging it here real quick. Let's see what I'm doing wrong. Well, so this one here. Oh, I have two. Yep. Okay. So children as the function here and children as a property here. Yep. I screwed that one up. Yep. So this should be, let me rename this one here, because this one should be private. I shouldn't have left that one public here. That's my mistake. Let's rename that one to underscore children, right? That's a private children value here. Okay. And hopefully that fixes it. Yep. All right, maybe that'll work here. Let's see. Run. Oh, nope. Okay. Oh, it refactored that one, of course. Dot children of, okay. Print the child. All right. Okay, cool. So now we're getting positions. Child dot data, right? And we can get out the value at each one. There we go. Okay, cool. We're getting closer here. Okay, that was just a naming error. My mistake. Okay. So this is working pretty well here, I think. So again, this yield says give the one here and then wait until you ask for the next one. So this loop just kind of sits and chills there. Just kind of hangs out until we ask for the next one, and then asks for the next one, and asks for the next one. Yeah, thanks, Lost. Yeah, that was silly. I wish there was a way I could give you like bonus points. That would be cool. That would be really fun. I don't think I can do that though. Okay. Cool. So we got children then. The other ones we wanted to do. Sorry, I'm following along here. Getting there. Okay. Children. A position gives us all positions of the tree. So that one there is fun. So if you want all the positions of a tree, that one actually kind of depends. That one is a little bit harder to do. We'll talk about it. We'll try it here. So let's define positions given self. Right. So it should give every item as a position. Right. And to do that, I need to ask for myself as position. I need to ask for my children as positions, the children's as positions, the children's as positions, and on and on and on and on and on. So it goes a little. The idea it's going to be recursive, right? If you think, okay, this is how I'm going to give you all of the positions in the tree, because I have no way of knowing how many generations I have. I can't really do this very easily in a loop here. So let's see. Let's do that. More positions. Come on. Okay. Let's see. Where's my good one here? Sorry. Still looking for it here. Make sure I'm doing it the right way. Okay. Oh boy. Okay, this is fun. So we're going to, we need to give ourself, and then we need to go for every child. We need to also do that as well. Okay, so the idea is we're going to yield a self.position of self and self. And then for child in self.children, we want to actually have it recursively call itself. So it's going to yield itself, and then it's going to go through yield all of its children. So we want to say for child in self.children, we want to yield child.positions. No, I'm sorry, that's not right. Self.children. Is that right? Because we want to, let's see. Because that should give itself, and then it should call all of its children. This might work here. Let's try it. Let's see what we get. Let's say, so for position in root.positions, let's print position.data. See what we get. This might crash on us hard. Ooh. Position. Isn't it data? No, it's data. Root positions. Yield a position of self, and then for child, oh, that's right. Okay, so we need to call it self. Child position. So let's Those aren't positions here. That's the problem. We're getting there. We're getting there. This one is fun. This one is fun. That's right. We need to be tracking. We need to be tracking the position here. I can get the children out here. So give myself, and then for every child and children, give that one. Self.children, so that's the position to yield child. Oh, that's not going to do it though. Child dot. Oh, I'm missing that recursive wrapper. I'm sorry. Let's see. Let's see. Yeah, it's to consume the child position before yielding it. That is there. Yep, generator. Let's see. So for every child in that position, and okay, let's see. I think I need this helper one here. Fine. Positions. No position? No, that's not right. I already have the children one. Yield self dot. Children of the child. No, that's not right. Getting myself mixed up here. I'm sorry. Position. Lost, you're amazing today. Position, yield the position. Yeah, I want child positions. Yeah. Then for position in, no, that's no problem, Lost. Glad you could come. In child dot positions. See, but children, so that one's not a tree. Shoot, this needs to happen. That's our problem. This children needs a position. Position. Self dot, yeah, children is not giving itself. Okay. Self dot root. We can give it the root here. That should be us. We'll get every child in that position. And then for every child, we need to get all of its children. Child dot children. Given itself. Yield position. Yield position. Oh yeah, live coding is lots of fun. Live coding is a lot of fun. Position has no untreated children. Self dot. Can I do that? Oh, a value error. Container's not self. For our position. Do we need, I guess we need to keep root here. Yeah, so child tree is self.validate the child. And then for I'm losing my other loop here. Then we can use the tree to get the positions out. We're going to call child in child tree dot children child dot positions. No, I'm just going nuts here. I'm sorry, folks. This was no good. It's harder on an entry. The other ones are a lot easier. Shouldn't have picked the entry first. We're going to get ourselves, and we're going to get all the children. And they want to recurse. Alright, so for in self.children. Yield child.positions. I don't know if that's going to work either. I want to get all the children. And then I want to call it recursively. Self.position. Self and the child. Root and the child. And then we call that. Is that it? Aha! Maybe. Oh my goodness. Okay. Let's see. So what do we get here first? Where do we get all of these values? We're getting out a bunch of garbage. Are we getting the right ones though? Let's see what we got. Run this in debug mode. Giving everyone a headache. I'm sorry. Giving myself a headache too. The other trees are a lot easier than an entry. I'm sorry. This was a mistake to start in this one. Okay, so we're going to give ourselves back as a position. That position's data. Lab 1. Oh, wait. Root? That shouldn't be called Lab 1. Why are they giving me that one? Tree value. Self. Tree. Values Lab 1. Why did we get Lab 1 first? Oh, because we're skipping that one. Shoot. Let's see the position we get first. So here's the root here, our tree. It has no parent. There's its value. It should yield itself as a position. We're the container. We're the tree. And then we yield it. Oh, good. Okay, so now we got that one. So we get our data back out. Our value here. Tree's value is that one. Okay, so we print that one. We get the next position. Now we're going into each child in self-children. We're going to create a position of the child. Return the position. So the first position after that was lab 1, right? Which is, right, we added lab 1. That was the first child we added. It's a good sign. Get the data. Okay, now we're going to the child positions. We didn't do anything with it, that's right. We want to give that one back. That's what we want to do. Here we go. Let's do this. Let's add a subtree pre-order given a position. There we go. So we can yield the position. Then we can go for child in self.children of the position. We can say now for subtree in self.subtree preorder given the position. And yield the subtree. Okay. Then we can give ourself, and we can go through this one. Self.root. Yield the child. Let's see. Oh, geez. Maximum recursion depth. All right, we broke it. Went too far. We're getting closer. The first parameter self position, always the root or the parent node. Self position. Yeah, self position should be the root, right? With the container that it belongs to. Self.root. Oh, maximum recursion depth again. Hey, we're just having a bad day today. It is not going well. Give me a second. I gotta go start some piano lessons real fast. Actually, let's see if my wife is doing that. Oh my goodness. All right, nope, she's got the little guy. I'll be right back. Let me put on some music for you. We will fix this, I promise, or just switch to the easier tree, because this is going poorly. I apologize. I'll be right back. Hey. All right. We can get this to work. My apologies. We're logging through all this. So this line here is bad because the first thing it does is give you the first one. I don't want that line. So I just want to go through every child, starting with root. Let's do this thing. We'll yield that child. And what that does, now I should yield the position. So it should start with root, and then for every child in that one, it should go through and yield those. Let's see. This one might work for us. Nope. Still broken. We're getting close. Sorry you guys have to be sitting through this. The entry one should not be this hard. Should not be this hard. Yield the child. Yield the position. For every child in that position, we should yield it again. Nope, nope, nope. That's the wrong window. PyCharm. This one here. Starting with the root, yield all the children. Children yield that. Subtree, we yield the subtree. Should give us the position, and then its children. Where is it breaking? Need children in that position. Let's see. Let's see where it's breaking. Why is it not moving to the next one? So it should give me every child in root. It should yield that child. The root should give me itself. Then it should go through its children and yield the children of that one. Something wrong here, obviously. The most inner call goes back to the position instead of the child's position. And Lost, you are on fire, my good sir. Hey, how's it going, Dodo? All right, so we're giving root. Okay, so we've got the root. Oh, you know, this demo is going terrible, but that's okay. So we're going to give back root. That's good. Step. Oh, that's where I broke it. Nope. That's right, we broke it there. Yep. Most inner call. Go back into position. The child. Child. Yeah, that's a typo. Thank you, Lost. I am lost, my friend. I'm lost. Value errors. If the container is not self. So for a position. Oh, because our parents aren't. So it's not validating right when we validate our children. Because it's expecting when we validate that, what do we say here? That the container is itself. The container should be self-root. Not even root though, right? Root dot. Because root is going to give us a position. We don't want that. We want root tree. So the root tree? Nope, still giving us errors here. We're making these containers, these positions wrong. Child. We make position, given root and the child. Should have done this with an entry, folks. I'm sorry. This is just my mistake. My mistake doing this with an entry. It should always be the root, the container. and then the child. I wonder where it's breaking there. Positions, subtree for the child position. Let's see if we can find it. This is interesting. We're getting closer. And it'll be much easier when we do our other trees, I promise. This one is just being obnoxious. So we'll step into positions. Turn our position. Okay, so we have root. We're going to yield that position for root. And we're going to go now for each child. That was it. Go to the next one. Printed the data. Okay. Define root. Oh, it does put itself there. You're right. No, yep. So root is bad. So root needs to go all the way up to the parent. There we go. So self dot current is self, and while we can just say current dot parent is not none. Current equals current dot parent. So that should be our root. Is the container and itself. Is that it? Maybe that's it. No. Still failing its validate. Well, if we want root, it should be it's the tree. The tree is its container, and the tree should be the root of the tree. I think so. Oh, we're doing something else bad, I think, with these positions. It's not validating. So all the positions should have the same tree root. And all this time debugging. Sorry, folks. Let's see. Step or root. Okay. Now we're called here, so we're going to yield ourselves. And we go to the next child. That was it. Okay, we get the data out, and we've printed the top level. We printed the root. Let's keep on going. Now we've done root. Right, we did that one. Where's our call stack? Did I miss that one? Let's see the call stack. Ah, here. Okay. So now we're in here. We're at 70 in positions. Let's keep on going. Okay, so we've yielded position. Now we ask for the next one. So now we're back in. Let's get the children of the position here. And that position is our root tree. It's a good sign. So then we're going to ask for the children of the root. We validate. We get our root out. Okay, that's good. We give them back the tree. Now we have the current tree, again, is us. That's a good sign. And now we're going to look for the children of our tree. And let's see. The first child in our tree, right, is lab 1. We're going to yield lab 1 as a position. Okay, so now we have child here. So child should be lab 1. Yep, child is lab 1. It's a good sign. The return none. If we're empty, we should never get to empty though. I don't know. So we're going to subtree. We're going to recursively call ourselves, right, with lab 1. So lab 1 says, okay, yield lab 1. Great. We yield the child. We get lab 1 out. We printed lab 1. Well, we didn't print lab 1. What did we print? 461. That's 461. Should be lab 1. And we're going to ask for the next child. So we're back here. Right, we just yielded. We're ready to go to the next one here. So our current position here in the call stack. Back at root. Looking at the next child. Get the next child out. Validating the next child. Make a position. Crashed there? There's our value error. That was at the next position. That should have been the child after lab 1. And we broke it. Should not have started with entries, but I really want to finish entries now. I want to make this work. All right, we're getting our self. Okay, so we yield our self, and we print position data. Winter, okay. We go to the next position in positions. Going through every child. We're yielding the child. So yield a position. Now we're going to look for children of the position now is root here. So we should be able to find all of its children. So we're going to look for every children in root. It's validating. It is the same. We make a position. Okay, now we have root. We're going to compare ourselves to root. So the positions container should be root, and self roots, right, should be that same one. So this one was good. We return the tree. Okay, so now the current tree is the root, and now for every child in the current tree, we're going to go make a position. With root as the container and the child as the subtree. What did it say? I missed that one. Making root again. Okay, so now we should have a child. So our first child, right, was lab 1. Its container was the root. That's good so far. We're yielding that child. So now the next position that we're yielding here then is the tree of lab 1. It's a good sign. And its data should be trees. Oh, it's value. That's, yeah, value should be lab 1. Okay. We should print out lab 1. I don't know why it's giving me numbers here. That's really weird. Don't know. All right, let's go look at the next one. Now we're going to the next child here in the pre-order. So the next subtree, so the current child tree is lab 1. We're going to look for recursively now lab 1 here. So our position is lab 1. We're going to look for every children in lab 1. So we'll validate the current tree as our position here, right, is lab 1. It is a position, and its container for this container here should be the root. Why did I not like root? Position had a container. Roots tree. Here. That's a tree. I'm looking at the tree, like the tree object should be the same internally. Right, self-parent here, right? They should be the same location as roots. Tree should be the parent object. That position's container. That looks right. So here's the tree object here. It's self. Not giving me the memory address. Hey, Blowfish. We are having a terrible day today, trying to get this entry to work. It's one of those days. Root. Roots tree. So I want to see, is that root tree the right one here? You know, can we just skip that for now? I just skip it, will this just make it happy? I just want this to run. Hey, look, it runs. I skipped my stupid validation. That's terrible. Why is that not validating right? Right? Right, my container should be the root every time. I don't know. I'm not really sure. So we get this one, we get lab 1, and we get the next child and its children, and then we get the last child, and it doesn't have any children. I'm going to call this good for now. This is terrible. I'm sorry, folks. This is why this stuff is hard. And that's okay. To show, define root. Yeah. So root should be a position given current where we walk up until we have no parent. And we're probably never is empty, because is empty means we... Where's our is empty? Value is none. And we always should have values. Yeah, I'm screwing something up trying to grab that. But okay, we're iterating now. That was the whole goal. Position container was the position of root. That one ends up in self-root tree. Well, container should be, where do we make positions? Where do we make positions? It should be a tree object. Oh, root is a position here. Yep. No, I was screwing that up. Yep. Okay. Position doesn't want roots here. That's the problem. We want the roots tree every time we do this. Yeah, you were onto the right track there, Lost. That was my bad. Because they are not... Yeah, okay, so can we put our validation back then, maybe? So we'll check if position dot container is not self.root.tree. Raise a, I don't know, value error or something. There, is that going to do it? It does it. Nice. Okay, that was the problem. Hey, thanks so much, Lost. This was fun. All these little things here, folks. Oh my goodness, we're almost out of time. So the whole idea here, right, we want to check to make sure we have the same root. Right, so walk all the way up, make sure we have the same parent tree node. Right? They should be the same. And I was comparing a position to the tree here because my root previously in here was giving you a position, not the actual node, the tree itself. So that's the problem. Oh my goodness. Okay. Whew. We got it. We got it. So we can iterate through. So the idea with this iteration here, right, I'm going to iterate through every node here, every tree. We'll call this tree, right? We'll call it, I don't know, subtree. And every time you go to a subtree, it's going to give you itself first. Then it's going to go get its children, and it's going to give you its children recursively here, every subtree there, which will give you that child. So we're not going to get the top level, and then the next level, and the next level. We're going to get the top level, its first child, all of its children, all of its children, all of its children coming back. So it's a particular ordered traversal here. And these are a lot easier to look at if we're not doing end trees. I made the mistake of sticking within our end tree, and now I feel bad. So the easier tree to work with is a binary tree. So let's go add a new Python file here. Let's focus on our binary tree. Now the idea with a binary tree is they're much simpler here. Binary tree, in that they have at most 2 children. Right? Binary being 2. Right? So with a binary tree, you have 1 or 2 children. You have a left and a right. And either is optional, right? You could have a left. Maybe you just have a right. Maybe this one only has a left over here. Maybe this one has something over here. Right? But you can't have more than 2 children. Sure, we'll just have one hanging out here. So this is a little easier. Right, so again, this is our root. Right, so the height of this tree then here, right, the maximum depth. So this is depth 0, depth 1, depth 2, depth 3, and the height, right, is the max depth. So the height is 3 for our tree here in our binary tree form. So we've got a lot of ways we could store this. So the easy way to store this then, because we don't need to use a list every time, if we only have a left and right, we know specifically how many we have, is we could use linked nodes. So we have a node with a left child and a right child. Right, so each node in the tree has a left and a right. And maybe they're none, maybe they're not none. Right, so imagine each of these as like a little box here. Right? You've got a left, you got a right, you have a parent, and then you have your value. So your parent always points back up to you. Its left points here. Right? Point up to our parent. Parent points to us. We have particular values. I don't know, like 7, 3, 9, 12. The values don't matter too much here at this point. Okay. So in a binary tree, we only have 2 children. And this will make all of that other stuff so much easier because we don't have to deal with some n number of children. I should not have started with that one. I apologize. Should have started with the easy one and then went to the n one. So, you know, we're about out of time. Let's talk about the project on Thursday then, and then we'll finish up trees. We're going to look at storing trees with linked objects. We'll build out our binary tree with our linked objects, and then we can look at alternative ways of storing trees from the chapter. Okay, this was a bit of a mess. I apologize. Hopefully it makes sense what we had to fix in here. If it doesn't, let me know. I'd be happy to talk about it some more. But right, the idea of making sure we actually get the real root here. This root gives us a position, but then we want to compare the actual tree. They're not the position itself to make sure that they're correct. Or, you know, maybe we could compare to positions too. I don't know. That's okay. We got lots of options. So we'll come back to binary trees on Thursday, and I promise it'll be a lot easier where you can only add a left and add a right. There's no add n number of children and have this n recursive. So we still have a recursive option here where we have to go into all of the subtrees and go left and right, but it's a little bit cleaner. Okay? All right, folks, it's been fun. Let's see if there's anyone else around who want to go pester. Maybe they're doing a better job of coding. Let's see. I want to do calculus, chemistry, just art. Someone's doing some clay, right? Glazing, pottery. That's what it's called, pottery. I'm going to pester a couple people. Or rockets, if you want to go look at rockets in a Kerbal Space Program. That one's fun too. Or someone's doing tiny RC car stuff. Oh, that sounds fun. Should we check that one out? Let's go check out the tiny RC cars. That one sounds fun. All right, folks. Today was a bit of a bust. I'm sorry. I will have more fun on Thursday, and we can go from there, okay? And we'll talk about the next project. Take care.
Is 130 motor any stronger?